Good morning, friends. Last so many lectures, we were busy in writing big equation, approximation, and then try to get some meaning out of it. What we did was, first we developed equations of motion. Then we segregated longitudinal equations of motion, primarily that involved u dot, w dot, and q dot. That is motion along x direction, motion along z direction, and pitching motion about y-axis. Right? From there, we went into development of perturbed equation of motion. And there we made a strategy, small perturbation. So we change u to this, v as v1 plus small v, w as w1 plus small w, and so on, with the understanding u, v, w in small letters, they are all perturbed quantities. From there, we developed perturbed equation of motion, which was typically in the form u dot equal to w dot equal to and q dot equal to the forces, aerodynamic forces, propulsive forces, and gravity. And there was a term like FAX, aerodynamic, FAZ, aerodynamic, MAZ, aerodynamic, apart from gravity term, etc., etc. Then what we did, we said, okay, let us be clear that FAX is function of motion variable u by u1, we non-dimensionalize this, alpha qc by 2 u1, then alpha dot, then delta E, etc. And for FAX, we said alpha dot contribution will be negligible. Similar thing we did for FAZ, said it is function of u by u1, alpha dot c by 2 u1, qc by 2 u1, then delta E. And similarly for M, we say this will be function of same variable there are longitudinal case, right? Then we expanded FAX using dimensional derivative, using dimensional derivatives, and we wrote FAX is equal to x alpha into alpha, xq into q, x alpha dot into alpha dot, although we neglected alpha dot contribution, xu into u plus x delta E into delta E. Similarly for FAZ, we again wrote z alpha into alpha, zq into q, z alpha dot into alpha dot, zu into u plus z delta E into delta E. And in continuation, m, you know it is m alpha into alpha plus mq into q plus m alpha dot into alpha dot plus mu into u plus m delta E into delta E. Then what was the next step? We substituted this expression in these equations and then found a stability matrix. And for solution or to find the roots, we put the determinant of that matrix equal to 0, and we got equation of the form A is 4 plus B s cube plus C s square plus D s plus E equal to 0, where A, B, C, D, E can be evaluated using these dimensional derivatives as well as flight conditions, right? And for longitudinal case, we have seen generally for most of the airplane, you get two pair of complex conjugates and one pair is short period mode that is where the real part large negative, and the other one again that is a complex conjugate which is a long period which is phugoid mode. All this thing we have done. Similar thing we have done for lateral directional case. There also we got equation of this form, and there when you do for lateral directional case, we found typically there are two real roots. One was spiral mode, one belongs to roll mode, and another one which is a complex conjugate, and that was Dutch roll mode. Okay? And we have tried to understand how to use approximation to get an idea about the expression of natural frequency and damping ratio. For all these cases, finally we came down to the expression for natural frequency and damping ratio. Why we are doing all this thing? Because from those values we will be able to understand, or from the roots of this equation we will be understanding whether the aircraft is dynamically stable in that mode or not. Further, the values of zeta, the damping ratio, and omega n will also tell us about the handling qualities of the airplane. And that will be dealt in the subsequent lecture, and during that only we will find the requirement of having stability augmentation system. Right? But you could understand one thing, if you are a designer, since your configuration is not completely ready, how do I get these equations? Because A needs complete detail of aerodynamic coefficients of the airplane, but your airplane is not fully ready. It's a conceptual stage, maybe plus one conceptual stage. So you need to look for some approximate expression. That is why those approximate expressions were evolved. But more than that, if I am a designer, I will first start with one-dimensional dynamics and try to get feel for some important numbers. And then I will go for the approximate methods, and then finally I will go for the exact method. Okay? So the approach would be for a designer, he first tries with one-dimensional method, then approximate. As you know, approximate methods are not very accurate, but it's useful, and then for exact solution. Right. Designer will be always happy following that path. So let us revisit when I talk about one-dimensional approach for analyzing one-dimensional dynamics, which is also you are familiar. And I thought since so much of expressions we have written, by now many of you might have even stopped seeing the lecture because so many equations are coming. And my role is to tell you that these are to be done only once. And as long as you know the final result, you know how to handle this. Let us see if I take a longitudinal case. What happens if a body is disturbed in longitudinal, then you know there is a short period mode and there is a phugoid mode. Okay. The short period mode will be governed by the static stability, that is Cm alpha, because alpha Cm counter. So, Cm alpha will decide, and Cm alpha short period mode will be decided by Cm alpha, and Cm alpha has direct link with static margin, because you know static margin is roughly dCm by dCl equal to minus static margin, and dCm by dCl I can write as dCm by d alpha into 1 by dCl by d alpha. Right. So, minus static margin, so dCm by d alpha will be approximately equal to minus static margin into dCl by d alpha. Right. And dCl by d alpha, if you see for an airplane, it will be between 5 to 5.5 or at the most 4.5 to 5.5. This value is saturated around that. So, as a designer, I can start picking one of the average number and take static margin as 10%, static margin as 10 to 15%. So, your initial value of dCm by d alpha to start with for this combination, static margin is 10% means 0.1, and CL alpha if it is 5, so this is 0.5 per radian. A typical value of Cm alpha of aircraft, small this aircraft, lies within that order minus 0.5 to 0.8 per radian. It's order of magnitude 1 per radian. So this is the importance of Cm alpha. And you are seeing the short period dynamics is decided more influenced by Cm alpha. Similarly, you will find Cmq also, pitch damping also will decide the transient or dynamics of longitudinal. We do approximation, we say, although I know that if this plane is disturbed in longitudinal plane by a elevated deflection, it will not only oscillate like this, but also have a plunging motion, because force is there, so there will be acceleration, deceleration like this. But we will neglect this. We say the time is so short, we will neglect this motion, plunging motion. We will only say it is pitching like this, which is equivalent to saying, which we have already done, that if I mount this airplane in a tunnel, and this is V, and this is the point where it is hinged, and only pitch degree of freedom, and you deflect it, the elevator, give a disturbance, and then it will go on oscillating like this. In such case, this is one-dimensional case because only pitching motion we are considering. In that case, how do I model it? That already you know, because I want to demonstrate you the advantage of dimensional derivative. So, you know, ideally I y y q dot or small q dot, let us say, will be equal to moment, which will be equal to half rho v square s c bar into Cm alpha into alpha Cm q into qc by 2 u1 plus Cm alpha dot into alpha dot c by 2 u1 plus Cm delta E into delta E. No problem. I have taken Cm naught equal to 0 to start, just to check the dynamics part of it, which by now you know can be written as q dot equal to m alpha into alpha mq into q plus m alpha dot into alpha dot plus m delta E into delta E. We have been using this, and you can see that what is m alpha? M alpha is nothing but half rho v square s c bar into Cm alpha by I y y. Similarly, you can find out MQ, M alpha dot, all these things we have done when you are dealing with bigger equation. Now see, once I know this, then I put in up, because there is only pitching motion, no plunging, so whatever theta is there, that is alpha, no plunging motion. So whatever theta, that is alpha, whatever theta dot equal to q equal to alpha dot, whatever q dot equal to theta double dot equal to alpha double dot. So I can now substitute in this equation, then I get alpha double dot equal to m alpha into alpha plus mq into alpha dot, because q is alpha dot, plus m alpha dot into alpha dot plus m delta E into delta E. So I can write this as alpha double dot minus mq plus m alpha dot into alpha dot plus m alpha into alpha minus m alpha into alpha is equal to m delta E into delta E. Right? Which standard form I can write alpha dot minus plus minus mq plus m alpha dot into alpha dot plus minus m alpha into alpha equal to m delta E into delta E. No problem, right? So what does this remind you? This is typically like mass spring damper system. So if I take a Laplace here, I get s square alpha of s plus minus mq plus m alpha dot s alpha of s plus minus m alpha into alpha of s equal to m delta E into delta E of s. Right? So if I write alpha of s by delta E of s, that will be m delta E divided by s square plus minus mq plus m alpha dot s plus minus m alpha. That's all, right? Okay. So what is this alpha s by delta E of s? This is called the transfer function. We have all learned this, transfer function. What is the advantage of transfer function? That if I know these values in terms of mq, m alpha dot, which I know based on aerodynamic coefficients and inertia parameter, I can easily find out what will be the alpha s for a given delta of s. I just multiply. Okay. And if I take inverse Laplace transform, I will get the time domain response. So if a block diagram, if you see, this is the transfer function, this is the input, which is delta U of s, it gives alpha of s, and then you go for inverse Laplace transform, you get alpha of t. Correct? This is one thing. Second thing we try to understand here, that what is the damping ratio and natural frequency for this pitching motion only, which is called pure pitch motion. Right. And that you could see s square plus minus mq plus m alpha dot into s plus minus m alpha equal to 0. This is the characteristic equation. And if I compare this with s square plus 2 zeta omega ns plus omega n square equal to 0. So I clearly see omega n is under root of minus m alpha, and 2 zeta omega n is equal to minus mq plus m alpha dot, right. So zeta will be minus mq plus m alpha dot divided by 2 omega n. Right. Suppose you are designing an aircraft, you need to have quick assessment of damping ratio. What you need is approximately the value of mq, that means you have already designed the tail, okay, and the CG of the aircraft you have got roughly, you have estimated. So using the lifting coefficient or lifting parameters of tail and this distance, roughly you can know the CMQ because of tail, and damping is primarily because of tail. And even if you take m alpha dot to be 20% of whatever CMQ value is there, then you get an idea of zeta, provided you know omega n. But omega n, you know, this is m alpha, this is nothing but minus half rho v square s c bar cm alpha by I y. So you know what static margin you are designing. From there you can get an assessment of cm alpha, maybe minus 0.8, and you know rough value of omega n, so rough value of zeta. At this stage you know whether you are close to the design requirement or not. It is possible that zeta you want around 0.5, but this is telling the zeta you are getting around 0.2. This is required, and this is basic. Okay. So the question comes, I want to increase the value of zeta from 0.2 to 0.5. How do I do? Immediately, I don't go to all these big expressions. No, not at this stage. I use this pure pitch expression for longitudinal case. I see, yes, zeta I have to increase from 0.2 to 0.5. So how much I have to increase MQ? That is, how much I have to increase CMQ? So before that, already you have got a rough value of omega n because you have designed for a particular static margin. So the moment you try to increase CMQ, you know you have to handle the tail volume ratio. That is, either you have to increase the tail size, or you have to this is horizontal tail, either you have to increase the tail size, say for example, CMQ when you are getting 0.2, tail area was like this, now for 0.5, you may have to either increase the tail size, or also you have to take it back. That is ST increase, LT increase, and the product ST LT by SC bar that you know, that is nothing but tail volume ratio. You have to increase, then again you reconfigure the design, again go for these initial estimates. When you are happy, fine. But if you find a situation where this enhancement of zeta from 0.2 to 0.5 is required occasionally, not all the time, right? Or if you want to increase from 0.2 to 0.5, which is little fairly large gap, let's say I was working for 0.4 and I want to go to 0.5, then if I am trying to change all those tail size, tail length, it is making a lot of problem for my configuration. So then the approach comes, can I do it online? And that is where the question comes, the stability augmentation system. That is, I need to increase zeta from zeta 1 and to increase it to zeta 2, omega n1 to omega n2, let's say for a longitudinal case. Then what is the procedure will follow, and that is what you are calling stability augmentation system. That is, will be artificially augmenting CM alpha, CMQ, and other derivatives, so that the zeta 1 goes to zeta 2, omega 1 goes to omega n2. But do not forget, this requirement is there because to maintain the flying handling qualities. You will appreciate the zeta value. Let's take zeta value. Okay, as a designer, now I'm talking like a designer. I'm saying this is approximately equal to minus mq by 2 under root minus m alpha. Right? 2 omega n is minus m alpha, and m alpha dot I have absorbed here. Let's say m alpha dot 20% I have already absorbed here. Right? Now you could see this zeta is also a function of now density of air. Because mq is half rho v square s c bar will be there, you know, and here under root. So it is function of density of air. So whatever zeta you have got at sea level, if you are going to a 10 kilometer, zeta is going to change. And that is where you have a question in mind. I cannot design my tail volume based on only one conditions. Right? What we will do for majority of the time, wherever the aircraft is in operational, we will try to get the zeta around that. And rest, the variations, we get it through SAS. So they are required to operate for different altitude, different conditions. Right? And that is the view. That's why we say online. Right? Whatever altitude is there, automatically the stability will be augmented. Okay? That is the need for a SAS.